Hello. Hi. All right, let's get this set up here. Okay. Hi, my name is Anjana Vakil, and I am from San Francisco, and I'm here today to talk to you about programming paradigms, or really programming across different paradigms. So I'm a software developer, but I didn't study computer science like maybe many of you have. Instead, I studied philosophy. So I really like to think about the big picture, abstract ideas that we use when we do our jobs as software developers. So that's what we're going to get into today. It's going to be really abstract, very philosophical, so buckle up, get ready. There is a version of these slides with all of the references and links in case you want to look them up later. Don't worry about taking notes. You can find the slides online at SpeakerDeck. So as I mentioned, I am a software developer. I work at a company called Mapbox. Has anybody heard of Mapbox? Used Mapbox? All right, yes, quite a few hands. Awesome. If you haven't heard of Mapbox, we make a live location data platform. We make APIs and SDKs to help you include maps and search and navigation and all kinds of other geographic data in your applications, on mobile, on the web, in VR, in all kinds of different things. So I'm happy to talk about that. If you have any questions or want to tell me what cool stuff you've built with Mapbox, come find me after the talk. This is not going to be about that at all. So I currently work as a software developer, but like I said, I didn't study computer science. So I took a non-traditional path, and I want to tell you quickly about some communities and programs that helped me get here to talk to all of you today. One of them is called the Recurse Center. This is a free, self-directed programming retreat and really great learning community in New York City. It's super cool. You can read all about it at recurse.com. And it's while I was at the Recurse Center exploring ideas about programming paradigms that I'm going to tell you in this talk. And there I found out about a really cool program that I hope some of you will check out that got me my first internship in tech, which is called Outreachy. Outreachy is a program to get more women and other underrepresented groups involved in open source by offering paid remote internships to people all over the world at organizations that work on open source projects, like, for example, Mozilla and many others. So if you or somebody you know is a woman trying to break into the tech world who's looking for a paid remote internship in coding, in documentation, in community management, all kinds of different things, please, please, please tell them to check out outreachy.org. And I did my internship at Mozilla. Mozillians are in the house, a few of us, and I'm still involved with Mozilla through a program called the Tech Speakers. Tech Speakers in the audience, represent? Where you at? Woo! Okay, you can catch my fellow tech speaker, Rizky, give a lightning talk a little bit later today. So we're happy to chat about any of those things after the conference, but as I said, we're not here to talk about any of that. We're here to talk about programming paradigms and programming philosophy. So like, what even is that? So when I was at the Recurse Center, I was doing some research on programming paradigms, and I found out that the first time the notion of a paradigm became really popular in the computer science world was through this guy, Robert Floyd, way back in 1978. So he won the Turing Award, the highest award anybody can receive in computer science, back in 1978. And the cool thing about winning a Turing Award is that then you get to give a lecture and everybody has to listen to you talk about whatever you want. What's cool is that I don't have a Turing Award, but you still have to listen to me talk about whatever I want, which is programming paradigms, which is what Robert Floyd chose to talk about in his Turing Award lecture. He dedicated his lecture to that because he thought that programming paradigms are the most important thing for us to think about if we want to make the practice of programming better. He says the best chance we have to improve the general practice of programming as a community of software developers is to attend to our paradigms, to pay attention to the paradigm level of abstraction. So, okay, I've used this word paradigm like 5 million times so far, and it's only minute 5 of the talk. What is it? What are we talking about here? What is a paradigm? So I first ran into the word paradigm when I was studying philosophy, and it was described in my philosophy of science books as being a kind of a worldview, a way of looking at and understanding the world. Now, what that world is depends on what your field of interest is. If you're a physicist, maybe the world that you care about is like the physical world, the physical universe. If you're a doctor, maybe the world you care about is the human body. And if you're a programmer, the world that we care about is the program or the computer and the programs that we write for it. So a paradigm is a way of understanding that world, or another way of saying that is that it's a model that tells us what that world is made up of, like what entities are in the world, and how those entities behave and interact with one another. So, okay, that means that a programming paradigm is essentially a model that's trying to tell us what programming is. It's trying to answer this question. What does it mean to write a program? What does a program contain? And what does the act of programming involve? And so different programming paradigms have different answers to this question. Imperative programming was kind of the first paradigm that burst onto the scene when the miracle happened and humans figured out how to take a pile of rocks and electrocute it and tell it to do what we want. And so we started writing imperative programs in languages like COBOL, that's Laura Wrightson, and C, and later C++, and now cool stuff like Rust. So who writes imperative code? Anybody? Lots of hands. Okay, cool. So in imperative programming, the program is essentially thought of as being made up of commands, imperative statements, imperative commands that say, do this, and then do that. Put this number in memory, and then add it with this other number, and then retrieve the values, etc. And so programming becomes giving commands to the computer and saying, okay, computer, do what I say, follow my commands in the order that I give them. Order is very important, and that's because we are changing values in memory over time. That means we are maintaining state. And so this is the model that imperative programming gives us of what it is to write a program and what a program contains. Now, I like to have visual metaphors for these very abstract ideas, and I think a great visual metaphor for imperative programming is a really complex machine like a clock or a watch. You've got all these little pieces. They're sort of like the commands that we're slotting in. They have to all be in the right order, and they have to all be working together. And if we get one wrong, the whole thing is probably going to grind to a halt and stop. So if there's a bug in one part of our code, the entire machine might stop. And so this means that writing really big, really complex systems in an imperative style can be difficult because of that state. And so other paradigms were invented to try to model the world of computation and programs a little bit differently to help deal with that. So one such alternative paradigm is object-oriented programming. Anybody write object-oriented code? Lots of hands. Okay, cool. So this is, we write object-oriented code in, like, I used to write Python, or Ruby is a good one. Java is arguably object-oriented. We can talk about that in the hallway later. Anyway, in the object-oriented paradigm, we're modeling the program differently. Instead of focusing on the commands and the order, what we're focusing on are little units of state that we call objects. And we're saying, okay, objects, you keep your values, your data, keep it private, keep it to yourself. Don't expose that to the rest of the program. And then wait for messages in the form of method calls, and then react to those methods calls, those messages, however you think is best. Maybe it's using your own implementation. Maybe it's using a parent class's implementation. And so respond as you see fit to those messages that we're passing with method calls. I'm not going to go into detail on this, but the notion of message passing in object-oriented programming is something that totally blew my mind when I found out about it by reading some writings of Alan Kay, who created the paradigm. There's references in the slides later, which you can take a look at. I'm not going to go into it. But to suffice it to say, Alan Kay is often thought of as like the father of object-oriented programming. He also studied things that were not computers, including biology. And the metaphor that he liked, and that I think is a great visual metaphor for object-oriented programming as a paradigm, is cells, like cells in a body. The way cells make up tissues and organs, and those make up a body, is kind of how objects make up other objects, which make up a program. And just like cells, these objects, they have a membrane that protects them from the outside world. They keep their little organelles and their internal DNA and things like that secret, private, and they communicate with each other by sending messages. In their case, it's by passing molecules, chemicals, across membranes, but that's a great analogy for the way that objects communicate by making method calls to each other. So what we have then is a much more organic and much more flexible model of programming than the rigid, mechanical, imperative programming model. So now, if one of our cells has a bug or it dies, the rest of the program can theoretically recover. The rest of the body doesn't necessarily lock up and crash. But this is not the only way of conceiving of a program. And of course, there are completely different models of computation. For example, functional programming. Anybody write functional code? A few, okay, all right, good number of hands, a little bit fewer than object-oriented, that's cool. So in functional programming, in languages like Haskell or Lisps like Clojure, we have a completely different model of what a program should be. Instead of thinking about programs as being stateful, where we have a series of commands and we're changing values over time, even if that state is protected and kept private in objects, in functional programming, we get rid of state entirely. We say, okay, state is dangerous. When you change or mutate values over time, you can introduce bugs. It can be unpredictable. You don't necessarily know what's going to happen. So instead of thinking about programs as being commands that change and manipulate and mutate state, we think about programs as being a composition of so-called pure functions, where a pure function is like kind of like a mathematical function where it gives you some output. And that's all that it does. It doesn't change anything else in the world. And that output is only determined by whatever inputs you give to the function. So it only looks at its input, which is going to be some data that's coming in. It does its computation using only that data, and then returns some other data, that output that it gives back. So these become kind of like little data processors. You get data in and data out, and you can chain them up together to make nice long pipelines to transform your data. So we're now thinking about or modeling computation as being a data transformation process instead of a series of commands. I think a great visual metaphor for this is an assembly line, like in a factory, where you've got one station, is like one function, that takes in some sheet metal and makes parts of the car, and then the next station bolts them all together, and then the next station puts on the wheels, and the next station paints it, and so on and so forth. And from those raw materials, eventually, they get transformed into a complete car. So now we're really looking at programming as being the act of transforming that data in the right way. Now, functional programming is kind of a sub-paradigm of a bigger umbrella paradigm called declarative programming, which people often use the language SQL as like a great example of declarative programming. So who writes SQL a lot? Few people? Oh, come on. I know more of you have to write SQL than that. Anyway, and also other languages like Prolog, which is another kind of declarative paradigm called logic programming. In this paradigm, it's kind of the opposite of imperative programming in some ways. So instead of giving the computer commands and saying, I'm telling you exactly how I want you to do this thing, we think about giving the computer declarative statements, like, here are some facts about the world, and this is the output that I would like to know from you. This is the shape of data that I would want. And we let the computer figure out the implementation. We don't really care exactly how it does it. We don't care the steps that it takes or the order it takes them in. You don't care exactly how your database performs the join on the two tables. Rather, you just care about what happens at the end. So this is kind of like doing a logic puzzle, like Sudoku. Anybody play Sudoku? Okay, all right, great. If you've never played Sudoku before, these are the rules. You get a grid like this. You have some numbers filled in, and your job is to fill in the rest of the numbers so that every row and every column and every square has all of the digits 1 through 9. So in this analogy, you are the computer, and I am giving you some facts about the world. There's a 1 in the top left corner, there's a 6 in the top right corner, etc., etc. And I'm telling you I want a completed grid with the numbers 1 through 9 in all the rows, columns, and boxes. I don't care if you write in the numbers left to right or bottom to top or in random order. I don't care if you use pencil or pen or if you make guesses. All I care about is the final product. So in this analogy, you're the declarative, you're the computer, and I'm giving you a declarative program to ask you to fill in this grid. Okay, so I've gone through a bunch of paradigms. Have I gone through all of them? Absolutely not. There's like a million. This is a chart made by someone who nerds out about paradigms even more than I do, a computer science professor named Peter Van Rooij. You do not need to memorize this. The links are in the slides. And it doesn't matter what's in here. Suffice it to say, there are many. This is not even all of them. This is just the principal programming paradigms. What he's done is he's broken them down in terms of the concepts that each paradigm supports. And he's charted them all out to show what I think is really interesting is that we have all of these different paradigms, these different models of what a program is and what the act of programming is. And sometimes we think that they're really, really different, like functional programming and imperative programming. The internet is like, oh, they're epic rivals, never the two shall meet. However, they might only be separated by 1 or 2 concepts that change the way those models work. So the point of all of this is that there's a bajillion paradigms to choose from. Now, that probably raises for many people the question, okay, well, which one should I use? Which paradigm is the best? All right, raise your hand if you think imperative programming is the best. Functional programming? Few hands. Object-oriented? Lots of hands. Declarative? Nobody. Okay, guess what? You're all wrong. So if we think about paradigms as models, we have to remember a quote by a famous statistician, George E.P. Box. He says, all models are wrong. This is true. A model is just a representation of reality. It is not reality. So all models are wrong. All models do not correspond to reality in some way. But at best, a model can be useful. It can help illuminate something about the real world that helps us do something that we need to do or solve a problem that we have. So I asked you a nonsensical question. We shouldn't be asking which paradigm is best or is this paradigm better than this one. We should be asking when is each one useful? What is it useful for? What can it illuminate? What can it help us do? So imperative programming is really great when we care a lot about the implementation, when we care a lot about how something is done, because we're concerned with performance or machine efficiency. Now, it's great to use imperative programming when you really need to drop down to that machine efficient level. Like, for example, maybe you're working in a functional language like Elixir, but you have some part of your program that requires very performance critical code. So Elixir, like many languages, allows you to write functions in another language and call them from your Elixir program through something called a native implemented function, or a NIF. In other languages, that's often called a foreign function interface, or an FFI. So you can write a function in an imperative language like Rust that does your implementation sensitive, machine efficient, fancy computation with whatever complicated math you need to do. Such imperative, so performance, wow. And then you can call that from your functional language or object-oriented language or whatever it is when you're no longer so concerned with the implementation and with that machine efficiency. On the flip side, declarative programming teaches us to think about the high-level abstractions. Think about the domain. What would a domain expert, what words would they use to talk about this? How would they think about this problem? So it teaches us to be a little bit more human efficient rather than machine efficient. And so one way that this often comes up is in domain-specific languages, DSLs. In many languages, like an object-oriented language like Java, you can expose a way of communicating with the program to your users that uses like a subset of the host language, Java, so it's called an embedded domain-specific language because it uses parts of the original syntax that allows people to program almost as if they're talking to a human. So here, maybe I'm writing a calendar application and I want people to be able to program their own calendar events using words that they're used to. So it doesn't even feel like writing code so much. It feels a little bit more conversational, a little bit more how you would talk to somebody if you were just describing, I want an event called SARCOM on this date, from this time, etc. So this is what declarative programming is really useful for. We don't care about the implementation. We don't care about how Java is like storing all of this and how it's going to create that calendar object. We just care about the high-level domain. Now, object-oriented programming is really useful when we need to encapsulate some information or remember information throughout multiple parts of our program. So for example, maybe I'm writing an API in a functional first language like F#, which is a .NET language that you can do functional programming in, but you do a little bit of OOP. And so maybe I'm writing this API, and I find that I have all these functions that have the same dependencies, but I have to keep writing these really long signatures every time, repeating myself over and over and over with these dependencies. Maybe it's useful to take an object-oriented approach to create an API object that remembers all of those dependencies so that then those functions become methods with much shorter signatures so I don't have to repeat myself this much. So that's one way that object-oriented programming can be useful. And on the contrary, functional programming can be really useful when what we care about is isolating parts of our program and thinking about it in terms of data transformation, like that assembly line that we were talking about. There's a great blog post by a woman named Jessica Kerr, who's a software developer and also manager. And she says she was trying to whiteboard a problem that her team had, a system that they needed to build. She was trying to whiteboard it in an object-oriented style. I think they were writing it in Java or something like that. And she had a really hard time writing this whiteboard diagram. It was really difficult to keep everything in mind, and there were lots of like backwards arrows. It was also difficult to see how you could chop that up into different parts that the different members of the team could go work on and then bring back together. She says when she forgot about the object-oriented way of thinking about it and moved to a functional way of thinking about it, she reframed the problem as data transformation, and the diagram just became so much simpler. And it became much easier to chop it up into little parts that could all be isolated and passed off to individual team members who could go implement them and then bring them all back at the end. So my point here is that each of these paradigms is useful in certain situations. Peter Van Roy, who made that big diagram, he puts it like this. He says, each paradigm supports a set of concepts that make it the best for a certain kind of problem. And this is really my point here today, is that we shouldn't think about paradigms as being good absolutely. we should think about them as being a good choice for a particular problem. And that means that it's a really good idea for all of us to learn as many new paradigms as possible so that we have as many choices of different tools in our toolbox for all of the problems we might encounter. And as a community, it's important that we always keep thinking about new paradigms we could invent, new solutions we might have to problems that our existing toolbox doesn't solve very well. So let's all take a little time to step back once in a while and attend to our paradigms. So terima kasih, thank you very much, Sarkam, and thank you all of you. The slides are up here.